Imagine that you were asked at GCSE to draw a dot and cross diagram of sodium chloride. What you might have produced is something that looks like this, and actually this is a decent dot and cross diagram for sodium chloride. But there's a little bit of a flaw in the plan here, because of course sodium chloride is not just two isolated gaseous ions like we've drawn in the dot and cross diagram. Sodium chloride is a giant ionic lattice structure containing 1 mole of sodium ions and 1 mole of chloride ions for 1 mole of sodium chloride. Moreover, sodium itself is not isolated atoms, it's a giant metallic lattice. And chlorine itself does not exist as isolated gaseous chlorine atoms, but exists as Cl2 gas. So if we wish to get to the stage where the sodium atoms form sodium ions by transferring their outer shell electron to the outer shell of a chlorine atom to form chloride ions, then there's a bit more going on than just to say that it happens. In thermodynamics, what we do is we treat this as a series of individual steps and use something called a Born-Haber diagram to illustrate those steps and stages. This is the Born-Haber cycle for sodium chloride. It's not labelled up properly yet, but just to give you an overview, that's what it looks like. And when we've filled it all in, it will look like that. So let's take this step by step. And the first thing to notice is in this diagram that there's one place in the Born-Haber diagram here where there are arrows going both up and down. So we will use that place as our starting point for each of these discussions. At the bottom of the diagram here is 1 mole of the ionic solid in question. So Born-Haber cycles are always drawn with an ionic solid in question. So 1 mole of that solid ionic compound goes on that bottom line. And here at our start point, we've got the constituent elements needed in order to make 1 mole of that particular ionic solid. Let's zoom in a little on the bits of this diagram. That first line where we started off. So we're going to prepare 1 mole of ionic solid from its elements under their standard states in standard conditions. So the change in enthalpy that refers to is of course the standard enthalpy of formation for sodium chloride, which you've met previously earlier in the year. So in order to produce that sodium chloride, what we'd like to do is produce it from its constituent gaseous ions. So at the top of that arrow, in a few minutes time, we should see Na plus gas and Cl minus gas. And that enthalpy change then for the formation of 1 mole of the ionic solid would be the standard enthalpy change of lattice formation. So making that lattice. At the left hand side then we've got sodium solid and half Cl2 gas. The first thing that we need to do is deal with the sodium solid and make that into isolated gaseous sodium atoms. So take 1 mole of solid sodium, make 1 mole of gaseous sodium. That's the only change that's happened on that line. And that's the standard enthalpy change of atomization of sodium. Now notice some convention on this diagram. The positive values, that's the endothermic changes, have arrows pointing upwards. Negative changes, that's exothermic changes, have arrows pointing downwards. And it's unsurprising that the standard enthalpy change of atomization of sodium is a positive value because that refers to the breaking of the strong electrostatic forces of attraction between the sodium ions and delocalized electrons within that giant metallic lattice. So that kind of makes sense. Let's keep moving through the diagram. My advice would be, if at all possible, do everything you possibly can to the metal ion first, then refer back to the non-metal and do everything you need to do to the non-metal to make the ion for that, and then bring those things together. So continuing with the sodium. So we've got sodium gas and half Cl2 gas. We need to make some sodium ions, Na+, which means that there needs to be 1 mole of electrons removed from 1 mole of gaseous sodium atoms to make 1 mole of gaseous sodium ions, each with a +1 charge. And a half Cl2 still needs to be there on that line because it still exists. It still needs to be part of this fully balanced cycle. So we just sit that on the line there. So of course that enthalpy change is the first ionization energy of sodium, and again likely to be endothermic because we've got to break the forces of attraction between the nucleus and that outermost electron being removed. So now we've got to the stage where we have Na plus ions gaseous. Brilliant. Now we need to do everything we can to the chlorine, the half Cl2, to produce Cl minus ions, and then we're off. We can make this ionic compound. So the first thing we need to do is convert half Cl2 molecules into 1 mole of Cl gas. So 1 mole of gaseous chlorine atoms being produced from a half a mole of gaseous chlorine molecules, Cl2 molecules. Again, likely to be endothermic because that's overcoming the force of attraction between the nuclei and the shared pair of electrons, in other words, breaking the covalent bonds, so that makes sense. Next change then is to change the chlorine atoms into chloride ions, just like so. And in doing so, each of those chlorine atoms has gained an electron. So the standard enthalpy of electron affinity of chlorine is the next one. This time, notice that's a negative value. And this is because this represents the formation of attractions, the attraction between the nucleus of that chlorine atom, the positive bit, and the additional electron. Formation of that attraction releases heat, so a negative change like so. And just to recap, we're now completing the cycles. So the Na plus gaseous and Cl minus gaseous are sort of off to the top right of this diagram. They would join together using the standard enthalpy of lattice formation. That would involve the formation of a huge number of strong electrostatic forces of attraction between the Na plus ions and Cl minus ions, so that we might predict is a downwards arrow and exothermic change. Let's have a look at the whole picture then. So this is the whole Born-Haber cycle for sodium chloride. Remember, we've got a starting point for this story, which is the elements in their standard states under standard conditions. So here, a giant metallic lattice of sodium. Here, half a mole of Cl2 gas. The sodium lattice breaks. The Na atoms gaseous lose 1 mole of electrons to produce 1 mole of Na plus ions and a mole of electrons as well. The Cl2 molecules have their bonds broken to form Cl gas, which then each gain an electron to form Cl minus, and that then can be represented by that type of dot and cross diagram that we looked at right at the start of the lesson. Those dot and cross diagrams, those positively charged ions and negatively charged ions, then attract each other ridiculously strongly, huge delta H lattice for NaCl to form our 1 mole of ionic compound at the bottom here. So why do we bother doing these diagrams? Why do we bother turning this into a story? Well, the whole point of this is that all of these different values are available experimentally. And therefore we can use those values together with the cycle and Hess's law in order to calculate any of the unknown quantities in actual fact. So by Hess's law, there are 2 routes that we could go from this starting point here to the end point here. So remember, this is the start and this is the end. We could choose to use the bright green route as I've coloured it here. So we could go individual steps and stages, get into the individual 1 mole each of the gaseous ions, which then come together using the lattice formation enthalpy to form NaCl. Or, alternatively, we could go directly from those elements under standard states and standard conditions to the 1 mole of the compound forming using the standard enthalpy change of formation for that particular compound. So by Hess's law, the plus 107, plus 496, plus 121, plus the minus 349, plus the standard enthalpy change of lattice formation, all adds up to be the same thing as minus 411 kilojoules per mole. Rearranging that, so the aim of the game here, the question marks with the standard enthalpy change of lattice formation for sodium chloride. rearrange that calculation to get minus 786 kilojoules per mole. And we would certainly expect that to be a negative value because that represents those strong attractions forming. So we can use this Born-Haber cycle idea to calculate all sorts of unknown thermodynamic properties, quantities should I say, based on data that we do know in conjunction with Hess's law. So have a go at the cycles for magnesium chloride now and also magnesium oxide in preparation for the live lesson.